Hello.
Sir, the PowerPoint is showing, but everyone is not in this meeting.
So can you just write a message in your WhatsApp that I have
Okay, sir.
restarted it
Okay, sir.
because it actually PowerPoint also went off automatically. I mean, MS Team also went off last time. Have you dropped the message?
Yes, sir.
Is the presentation visible now?
The threads in OS part, yes, sir. The whole window is visible.
Okay. So I think you have dropped the message right there
Yes,
in the
sir.
WhatsApp. Let's see.
Yes, sir.
Something went wrong. First the PowerPoint went off and then the MS Team.
So now is it working properly?
Yes, in my part there is no problem. Actually, it automatically went off the MS Team. Okay, now yeah, they're joining. Okay, let me wait for another a couple of minutes so that others are able to join. Hmm. Switch on the recording. Hmm. Okay, so what we are discussing about, so when we use multiple threads, the communication becomes very simple. As like different departments, if you have got multiple programs in the same department, communication among the among a student of say CS BTech and say BTech IT and BTech CS becomes very easy because they are all part of the same department. They can form groups to solve some projects. They can opt for guide no matter uh, because all the faculties are from the same pool, so the communication becomes very simple. They can use the same notice board, but the problem is whenever you have got a shared resource like this, whenever the resource is shared and you have got multiple threads which are having the access to that resource. So in this case this is a global variable, say x. So if some thread writes on it and some thread reads from it and another thread also writes on it, so the point is this part will be a topic of the next the next topic, this particular problem, that is of data access synchronization. So when you have got a common shared data and you are allowing multiple execution units, it may be threads or processes, to read write on that, there it might lead to anomaly. So we can have that example in details later on. So when you are trying to use threads in terms of the common global variable, this is not safe and this is not so easy to use also. So creating that shared space is easy, but using it in a proper way without any conflict or to make things consistent, you have to take a bit of pain. So you have to use synchronization primitives like semaphores and all to do that. So we'll see that later on how to resolve it. But right now you should be happy that at least you don't have to use the files to pass on information or whatever you have computed. Each thread can directly communicate to the parent thread if they have got separate variables for them stored, right? So this is one advantage, and let us enjoy the advantage till we know the problem that occurs and how to solve it. So thread libraries started appearing in the mid 90s, and as you can see here, these POSIX threads, the one that we'll be talking about in Linux. So POSIX is a standard for having portable codes across different operating systems, which supports Unix like philosophy, Unix like designs. So as you can see, FreeBSD, NetBSD, OpenBSD, including Linux, Mac, Android, so they all support POSIX thread. So if you write some application using POSIX thread library, as we'll do so, so you can simply use that piece of code anywhere or in any type of these operating systems because these are POSIX compliant. Okay. And until, so that is from the software part. Until 2000, most of the desktop computers are just using one core, single CPU. And from 2002, Intel started adding support for multi-threaded, so hardware-based multi-threading in Pentium 4. And 2005 onwards, this Pentium D or dual core or like multiple cores start coming. And these days, these are pretty common. Even in smartphones, you will have the multi-core facilities. So hardware level support for threading came a bit later, almost after another decade, but the thread level APIs started appearing from mid 90s, and they are a part of Linux these days also. So now let's come to the different possible approaches of operating systems towards threads. So this is one extreme, that you can see that one process. So box is a process, and this is what we show, this spiral, I mean this freehand drawing is meant for the execution thread. Okay, so one process, one thread. What is the example of it? MS DOS. It was a operating system that we used in our college days. Probably we started with MS-DOS. Okay, then gradually switched to Unix a little bit and Windows. So like that. So this is the MS-DOS is having one process, one thread. Then you can think of traditional Unix also. Traditional Unix, right from the beginning, it has got the facility to fork another process. So there are multiple processes that are supported in an application, but there was no thread support. Multiple thread support was not there. So one process, one thread. But you can have multiple processes coexisted in the application like this. Okay. Now, when you came to this, one process can create multiple threads. The example can be Java runtime, where you have got one process. You are basically not creating a separate process, but whenever you need parallelism, whenever you need concurrency in execution, you create multiple threads within the same process. Okay. And another extreme is like you have got multiple processes, support for creation of multiple processes, and within each process you can have multiple threads that you can create. It's a multiple process, multiple threads per process. That is a Linux kind of thing. Okay, so these are the from the OS perspective, these are how you can visualize the coexistence of threads and processes in terms of the OS designer, in terms of the OS design or the applications that they run. Okay, so I think this part is simple to understand. So now let us come to the different scenarios, application scenarios, where you probably need uh, such multi-threading. So one is the web server. So web server, we know that there's a remote client which is running a browser. From the browser you can use HTTP to provide to send some request to a server whose address you type on the browser address bar. And web server is nothing but it is hosting a set of web pages which are HTML files, that you can say it's a bulk of HTML files, and they have got hyperlinks from one to the other. So it's a kind of networked, it's a uh, connection of and a collection of HTML files. And if you put a particular specific address of a particular web page in a particular web browser from a client site, that means we are running say this Chrome and all these are client browsers. So they send the request to the remote server. So through the TCP IP it goes to the other, and then the server process, it is required to serve the request if it is a valid request. Okay, now there can be multiple requests that is coming to the web server from multiple clients. Now how the process, how a single web server process can handle it, this is not possible, because if the web server is handling my request, it cannot handle your request. And but these days it is really not the case. So a web server is capable of handling multiple and thousands of requests simultaneously. So there are two options. One is a web server, the original web server creates a separate process which satisfies a new user request, but this will definitely incur a lot of overhead. And instead of that, we can think of a multi-threaded web server. Whenever there is a new client request comes, so the parent thread just keeps listening to new requests. So if a new request comes, it will simply create a new thread of execution which will actually will be catering to the new request. So whatever you are asking for, it will be and again a new request comes, it will create another thread. And whenever the that particular browser gets uh, switched off, then definitely that thread gets off, thread goes off like that. So that is how the multi-threaded web server works, and there are reasons why we go for multi-threaded web server instead of having multi-processing, multiple processes created for it. Another is the text editor. So that can be one another typical example where you have got several activities to do. One is the automatic periodic backup. So we often find that you keep on typing, and you don't have to save, but it automatically gets saved after every, say, half a minute or maybe 10-20 seconds, right? Apart from that, it also goes for spell checking, for for the keyboard input also, that need to be, that is one task. And this grammar checking and all. So all of these tasks or subtasks uh, need to be done parallelly, okay, concurrently need to be done. And this can be done instead of, so in a text editor process, the text editor, to handle each of these subtasks, it can create just merely a thread, because they are all trying to come up with a single file, a written file. But there are different activities corresponding to that. So that's why instead of having multiple separate processes, child processes, we can consider separate thread of execution, each for one for each of these activities. So that way we can write. Web browsers also, like when we are browsing, uh, in my client side, maybe I'm browsing with Chrome. So Chrome have got multiple tabs, so maybe one thread is handling the request, even I'm in tab 4. The tab 5 might be displaying some video, tab 3 might be displaying some other song, I mean it's playing some other song, and tab 1 maybe still refreshing it, and it's continuing like that. So even for a web browser also, it can have a multi-threaded version of that, where whenever you create a thread, it just whenever you create a tab, that tab is handled by a separate thread of execution. So you don't have to again create another process. Computer games, different objects of the in a game which are active can be handled, because the algorithm or the actions of that particular object can be handled by a separate thread to make it faster. Video encoders, each and every frame can be, for encoding. So frame I and frame I plus 1 can be encoded separately, independently, by creating multiple threads to make things faster. So these are some application scenarios where multiple threads can be useful. Now there are possible, like from the designer's perspective, or the operating system designer's perspective, there can be multiple options that is there. Okay, so here what happens, the first option is a pure user level threads. So this is also very easy to understand. So pure user level threads is something like, you see, in our uh, in this particular section, we have got the fifth semester operating system, right? So what the academic section knows, the academic section, they know that there is a batch of 150 students, that's all. And the CS department will be handling this. So they will be taking the course of CSC 510 501. Now, do you think that the academic section is aware that we have splitted the batch into three subsections, CX, CY, CZ? Hello?
No, sir.
I mean, you probably are not aware, but the thing is, they say that we are not interested, whatever you do. So there is a department, you have got like 40 faculties, now you handle it in your own way. They don't even care about how many, so are they having joint classes, or like this time we have merged it because it's a virtual class. So they are not aware of it. So the existence of this CX, CY, CZ, each consisting of say 50-55 students, so this BTech third years, the academic section is not aware of it, so they just view it that as a batch 150 classes are going on. But the CS department, the departmental academic committee, they found it's too heavy to handle 150 students, and the policy should be, we should split it up into three subsections or three sections, and there will be one teacher assigned for each, or maybe one teacher taking all the class, all the three sections, but in separate slots, something like that. So can you see this? So this dividing into sections can be considered to be as creating separate execution sequences, or class, class sequences kind of. But this is completely not, it's absolutely not visible by the kernel, or I mean this is, in this case it is the academic section. So same thing happens here. This is a particular application process. So this application process, the kernel feels that is a keeps track, it's a single application process, but in the user space using some thread library, the user is free to create threads of execution, separate threads of execution, which actually exist in the user space. But the kernel is still, it knows that I have scheduled one process and I don't care about what threads are there or not. So this is pure user level thread application implementation. This is what the Linux type operating system using the POSIX library performs, right? So this POSIX library is a thread library which creates everything like this. So in such a situation, do you think that if a Linux scheduler or operating system kernel scheduler schedules processes, will you be able to take the advantage of multiple threads if you have in your user space? Are you getting my question? Have you got the analogy and what I mean to explain? Hello? 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 Can you hear me?
Yes, sir.
Have you got the question?
So
My
not
question
exactly,
is,
sir.
my question is, uh, in this case, do you think that even if you have got say two or three processors, two or I mean dual core or quad core, you have got one process, and in the process you have created three threads in the user space, right? So even if you have created three threads and you are having four CPU or processors, will you be able to execute them in parallel, all the three threads? Is it possible? Because a kernel is, after all, visualizing it as a single process at all, always. So without the kernel's help, how can you schedule or how can you assign a thread to a particular CPU? Are you getting the point?
Yes, sir.
Even
Yes,
though
sir.
there exist multiple threads in the user space, but the kernel still views it as a single entity. So the from the kernel's perspective, and if the kernel is not aware, it will not be scheduled. So the kernel is not scheduling a thread. That's most important. It's just scheduling a process like this p. And because of that, even if there are multiple cores, you will not be able to take the advantage, exploit the advantage of having multiple cores and run them parallelly. So this is one extreme. Another extreme, you see, it's a pure kernel level threads, and you can see the difference between of this here. So here the process itself is divided into multiple threads in the kernel space. So the kernel is aware of it, and the thread control block, the TCB, you see, so it is not only maintaining PCB, it is also maintaining TCB to keep track of the individual threads. Now it also knows that okay, these threads belong to this process, but it maintains it, it knows, it is aware of this what is happening. And in the user space also it is running like this. So these are user level application, but the kernel is aware of the three different threads of that application like this. So it is something similar to the first year courses. So the first year courses, this AXAY, BXBY, CXCY, so all the 8 sections in each semester, I think you are all aware of. So this has been, who has made the divisions? Institute academic section. So they were aware of these sections, and the department just takes care of each class, that's all. So here the point is the kernel, or in this case the academic section, they are aware of the sections, or the kernel is aware of the threads. Okay, so this is another possible implementation. So we call it as a pure kernel level threads, where the kernel is aware of the presence of the different threads corresponding to a process. So in this case, if you have to implement it, you have to go for kernel level threads. This is called KLT. This is called kernel level threads, KLT, and the previous one, it was called as ULT, user level threads. Okay, this is KLT, and this can be a hybrid one. So where you have got one process which is divided into two threads, and one process one thread. So here these two threads got split into three. That is also possible. So this is a hybrid kind of scenario where you have got a thread library. So the thread library might split or join some of the kernel level threads like that. Okay, so basically they will be splitting it further. So these two kernel level threads are further split into three of them. So it's just like you have got ax ay. The academic section says that I have defined ax ay as two separate sections for the first semester. But when the sessionals are taken, so the department finds that okay, sessional of say 50 100 students, we don't have more than 30 machines, so they will divide it into three subsections, a1 a2 a3, like this. Okay, so now this is a hybrid design. Now this academic section is not aware that the axay are having the sessional into in terms of three subsections. This is not, they are not aware of. So that is a kind of thing. But however, this theory, the 7 semester theory, the whole batch is considered to be a one unit in both the cases, the department and the institute academic section. So this is the example of hybrid ones. So these are the advantages and disadvantages. As you can see here, the portability of the codes uh, mm, uh, becomes, so in a user level thread it becomes highly portable, because the kernel is not, you are not changing the kernel, you don't seek support from the kernel. So if the OS is having a support for, it has loaded the POSIX library, you can run the same code in no matter what the operating system is. But portability is an issue in the KLT, kernel level threads. Okay, this is KLT and this is ULT. And the other advantages we just now mentioned, so implemented using POSIX thread library, and here it is implemented using the kernel itself. The kernel need to be redesigned for this. Thread scheduling in this is in the user space here, and here the thread scheduling and the implementation, everything is handled by the kernel. And it can exploit the multiple processor or the hardwares in the hardwares that we are having, because the kernel is aware of the three threads, and if it has got a quad core, so it can assign this one to one CPU, this one to one CPU, and this one to one CPU. And here the kernel is not aware, so even though there are CPUs, it is not aware of that, and it cannot exploit the multiple processors or hardwares available in the, or the cores available in the system. Okay, so thread switching here becomes less overhead, because when you are switching from this thread to this thread, you are basically not having a context switching the process in the kernel level, because they're all happening in the user space. But here in this case, a thread switching even within a same process, as you can see here, need to go for uh, the same overhead that of a process switching. Okay, and here if one user level thread is blocked, then the entire process will be blocked, because if one gets blocked means the then the kernel feels that the whole process is blocked, even if two other threads of the same process is ready for execution. But in this case it might happen, because the kernel is aware, so this is blocked, but these two still can run. So we can probably exploit the parallelism in a much better way here in case of kernel level threads, but you lose portability here. So you gain, so the advantage is this will be much faster, you can exploit the existence of multiple CPUs, but you lose portability, and thread switching is costly. So these are the relative drawbacks and advantages of this. Okay, so I've got just two more slides, then I'll continue in the next class. So one is when the parent creates a thread like this, it uses some POSIX thread library. One is a pthread create, this is a library, and whenever it creates two thread, child thread 1 and 2. So at some point of time, when the child thread completes, it will execute pthread exit. Okay, so you can think of this is something equivalent to the fork for creating processes, and this exit, this is equivalent to the process exit. Okay, and this join is something equivalent to the process wait. So here whenever the parent thread executes pthread join, it can synchronize with the child processes like this. So if this happens, that it creates and then again synchronizes, we will call it as joinable threads or attachable threads. And if it is not happening like this, if the parent is not interested in synchronizing with the child threads, we call it as detachable threads. Okay, so these are the two types, and I think it's almost 1 hour, so let me stop the class so that we can start afresh with the thread level library. I mean, we'll talk about the pthread create, pthread exit, and pthread join. These three functions, user library function, POSIX thread library functions, and we'll see that how they can be used to uh, create threads. Okay.